Welcome to today's Explainer. We're diving straight into a truly fascinating mathematical journey today, exploring the world of numbers and uncovering the absolute marvel of how we actually complete the number line. I mean, if you think you know your basic integers and fractions, well, prepare to have your mind totally expanded by what actually lies in the spaces right between them. Let's get into it. So here's our agenda for the Explainer. First, the rational number foundation, then the mind-bending density concept, and predicting decimals with prime factors. After that, we'll hit the shock of irrational numbers, look at the geometric square root spiral, and finally, unifying the real number line. All right, Section 1, the rational number foundation, defining the building blocks. So, to build up our understanding here, we really need to recall the core building blocks of our whole number system. And what's super interesting is the absolute strictness of the mathematical definition. A rational number is any number you can write in the form p over q, where p and q are integers. But, and this is absolutely crucial, q can never be equal to 0. That's the bedrock rule. Division by 0 is simply undefined in mathematics, so to legitimately categorize something as a rational number, that denominator has got to be non-zero. You know, this brilliantly shows how deeply our modern mathematical foundation is anchored right in our Indian knowledge systems. Back in 628 CE, the legendary mathematician Brahmagupta formally mapped out the arithmetic of negative numbers and 0. He beautifully called positive quantities dhana, meaning fortunes, and negative quantities rina, which meant debts. And honestly, this was a massive conceptual leap. It allowed us to confidently place both positive and negative rational numbers directly onto a number line, with zeros sitting perfectly right in the center. Okay, Section 2, the mind-bending density concept, exploring the space between.
Now, I want to challenge your intuition for a second. Think about this. What exactly is the next rational number after 1/2? Take a second to really think about it. Is it 2/3? Maybe 0.51? What is the immediate, absolute next step on that line?
Well, here is the crazy part. There is absolutely no next rational number. Literally none. This is what we call the property of density. Rational numbers are packed together infinitely tightly. Between any two rational numbers, no matter how microscopically close they might seem, there are infinitely many more. You can easily find them using the average method. Just add the numbers and divide by 2. Or use the equivalent denominator method, which expands the fractions to reveal this whole hidden neighborhood of numbers nestled right in between. Mind-bending, right? Moving on to Section 3, predicting decimals with prime factors, the termination test. Let's apply this knowledge practically. Did you know you can predict exactly how a fraction will behave as a decimal, and you don't even have to do the long division? It's true. By looking solely at the prime factors of a simplified denominator, you can instantly categorize its decimal expansion. Notice how, if the denominator's prime factors are made up of only 2s and 5s, the decimal will cleanly terminate, just like 7/8. But if literally any other prime factor sneaks into that denominator, say the 3 sitting inside 5/12, the decimal is going to be non-terminating and recurring. It is such a phenomenally predictive tool to have in your pocket. Next up, Section 4, the shock of irrational numbers, when patterns break. So what happens when numbers just flat out refuse to be written as simple fractions? Well, this caused absolute shockwaves in ancient mathematics. Let's analyze the famous proof by contradiction to see why the square root of 2 can never be a fraction. We start by assuming the exact opposite. We pretend the square root of 2 is a perfectly rational fraction, p over q, in its lowest terms. But as we square both sides and follow the algebraic steps, we run into a wall. We find that both p and q must be even numbers. And that is a massive contradiction. If they're both even, they obviously share a factor of 2, which means our very first assumption that they were in lowest terms was completely false. The whole pattern breaks, proving without a doubt that the square root of 2 is utterly irrational. And this brilliantly illustrates the porous boundary between what's rational and irrational. In the 14th century, the great Indian mathematician Madhava of Sangamagrama computed pi using an infinite series. Basically, he added and subtracted an endless string of completely rational fractions. But that infinite sum ultimately yields pi, a deeply irrational number that never ever terminates or repeats. It's just a gorgeous conceptual bridge showing how infinite processes can essentially break right out of the rational world. All right, Section 5, the geometric square root spiral, constructing the irrational. Let's dive into how we actually evaluate and physically construct these seemingly impossible, non-repeating lengths. We use what's called the square root spiral. We start with a simple right-angled triangle, sides of 1 and 1.
Then we apply the Bode-Pythagoras theorem to find the hypotenuse, which gives us exactly the square root of 2. By repeatedly adding a new 1-unit perpendicular line to the previous hypotenuse, we spiral outwards, physically constructing the exact lengths of the square roots of 3, 4, 5, and so on. Finally, we use compass arcs to basically sweep these exact lengths down from the center and pinpoint them precisely onto the number line. It's like building an intricate geometric puzzle piece by piece.
It's pretty incredible to realize that this specific geometry has truly ancient roots. Around 800 BCE, Baudhayana's Sulba Sutta provided a remarkably accurate geometric approximation of the square root of 2. We're talking accurate to 5 decimal places. They did this using stretched ropes, or raju, acting as compasses to draw precise arcs for complex altar constructions. That ancient rope and peg geometry from India is the direct, practical ancestor of the exact compass and arc transfers we use today.
And finally, Section 6. Unifying the real number line, completing the puzzle. Let's pull everything we've talked about together and look at the completed system. We finally arrive at real numbers, which we denote with the letter R. This is simply the union of all our rational numbers, so the fractions, terminating decimals, and integers, combined with all our irrational numbers, those non-terminating, non-recurring decimals like root 2 and pi. Together, they join forces to create the entire real number system. Let's make one final, really vital comparison here. We established earlier that rational numbers alone are infinitely dense, but despite that mind-bending density, they actually leave these microscopic empty gaps on the number line at exact positions like the square root of 2 and pi. However, by unifying rationals and irrationals into the set of real numbers, we completely fill the line. Every single geometric point now represents exactly one real number, ensuring there are absolutely 0 gaps left whatsoever. The puzzle is finally complete.
So the crucial question for you now is, how do you take all this conceptual understanding and actually turn it into exam-ready mastery? Well, I highly encourage you to visit edunudge.in today. Over there, you can access complete CBSE-aligned question banks and really tackle these HOTS competency-based scenarios head-on. You can use their unique 5-step nudge system to master everything from number line constructions to those complex irrational proofs. So head over to edunudge.in and start mastering the world of numbers. But hey, before you go, think about this for a second. If combining rational and irrational numbers completely fills up our one-dimensional number line, what happens when we add a second dimension? What entirely new world of numbers is waiting out there in the empty space? Thank you so much for joining me for this explainer, and as always, keep learning and exploring.